Hello everyone, welcome back to Technologies Discussion channel. This in fact will be the Series B discussion. On my Series A discussion, I have described the different types of line coding. For example, I have mentioned unipolar and partial of this polar. This video, I will continue on the polar, which is the Manchester and differential Manchester, and also bipolar AMI. So basically, this will be the objective of this video. This is my email. If you have any question regards on this discussion, please drop me an email. Before I continue, I'd like to urge you guys to help me by like this video. Guys, just a few seconds, help me press the like button now. For those who are new to this channel, and if you want to encourage me, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Let's take a look on the different types of line coding. Okay, as I mentioned earlier on my Series A discussion, I have discussed unipolar, which is one of them. The very classical one will be non-return zero. I have also covered the polar, okay, which is the non-return zero level and also non-return zero inverted. I have also discussed on the return to zero. So basically, this is all under the Series A discussion. This video, I will continue to discuss on Manchester, differential Manchester, and also the bipolar, AMI, etc. Let's continue on polar, okay, which has two equal but opposite voltage level. Okay, so let's focus on Manchester. So basically, there has a transition in the middle of every bit period. Okay, so what does this mean? Okay, so basically from this diagram here, you can see that at the middle, there always has this transition. So this is what you mean. There will be a transition in the middle of every bit period. So when the message is equals to 1, okay, basically we have from plus all the way move to minus. This is what we know as falling edge. So this is to indicate message 1. We are going to have a rising edge when the message is actually 0, which means that from minus move it to plus. Okay, so this is according to IEEE 802.3 standard. So later on, I will have an example to illustrate this. Coming to the Pro of Manchester, there won't be having any DC component. We are going to have excellent synchronization, okay, because right in the middle, we actually will have some form of transition. So basically, if let's say it's a string of ones or string of zero, we won't so-called become unsynchronized. So basically, with this Manchester, the key advantage will be having some form of synchronization. They are actually guaranteed because there will be having some form of transition for every bit. Coming to the negative, okay, so the bandwidth that is actually required is actually double, okay, because there's a transition right in the middle of the bit. So therefore, we are going to have double bandwidth incurred as compared to non-return zero. Basically, these are still used in internet, 10 megabits per second or RFID and NFC. Let's take a close look on Manchester. Okay, so basically, in short, this way, Manchester coding is basically a combination of RZ, return to zero. I'm not sure if you still remember. Okay, basically, they will have some form of transition at the middle of the bit, as you can see from here. Okay, and it's also a combination of non-return zero level scheme. Okay, the duration of each bit is divided into two halves. As you can see from here, they are actually divided into two halves, first half, second half. Okay, so basically the voltage remained at one level during the first half and moved to the other level in the second half. Basically, in short, you can see that there is no stopping at the zero line. Okay, so I like to highlight this. Basically, they move from either plus to minus or minus to plus. The transition in the middle of the bit actually provides some form of synchronization. Okay, let's take a look on example in order to understand better. For example, when the message is bit number 1, okay, I'm going to have from minus going to plus. So this is what we call the rising edge. When the bit is equal to 0, okay, I'm going to have transition from the plus to the minus, which is we know this as a so-called falling edge. Let's take a look on this example to understand better. So if the first one is attribute 0, so I'm going to move from plus to minus, as you can see from here, plus to minus. So basically, this is to indicate message 1. When message is equals to 1, I'm going to move from minus to plus, as you can see from here. minus to plus to indicate this is a message 1. Next, a message 0. I'm going to move from plus to minus. Again, from here, you can see that this is actually a plus to minus to indicate 0. Again, another bit is actually 0. So I'm going to move from plus to minus. Basically, this is how we move from plus to minus, or we know this as a falling edge. Okay, with this, I think you will be able to get this whole waveform. This is actually for Manchester. Polar, 2 equal, but opposite voltage level. Next will be differential Manchester. Let's take a look on the characteristics of differential Manchester. Again, there will be a transition in the middle. Okay, so this is for synchronization or for clocking purpose. The presence or absence of a transition at the start of the interval actually encode the data. I come to this with an example later on. Basically, if let's say that the next message is 1, there won't be any form of transition. Let's say the message is equal to 0, there will be some form of transition. Again, later on, I will use a time diagram to illustrate this on differential Manchester encoding. Coming to the advantages, basically for differential Manchester coding, they are actually more noise immune as compared to the Manchester because the data actually depends on transition but not on absolute level, okay, which I'm going to explain later on. So they are actually used in a token ring length. Let's come to a little bit more description on differential Manchester. Okay, so differential Manchester is actually a combination of return to 0 and non-return to 0 inverted skin. There is always a transition. Okay, return to 0, there is always a transition at the middle of the bit. As you can see from here, you can see that there will be a transition at the middle of the bit. So basically, this is actually the characteristics of return to 0. I'll come to the characteristic of non-return to 0 inverted. Okay, but the bit value are actually determined by the presence or absence of a transition at the start of the bit period. A transition at the start actually indicate a 0, while no transition actually indicate a 1. I come to this later on. Okay, so for differential Manchester in this example, okay, we assume the signal level before the start of the data sequence was positive, which means that they are actually positive. Okay, so which means that by default, okay, at the start, they are actually positive. Therefore, a transition can occur at the beginning and the first bit 0 in the current data set. Okay, I come to this. So basically, when the data over here, as illustrated, when the data on the next bit is equal to 0, okay, I will have some form of transition. When the data bit is actually equals to 1, I won't have any form of transition. So with this, let's take a look on this diagram to understand better. As I mentioned earlier on, okay, at the start here, basically will be a positive sign over here. The next bit is equal to 0. So therefore, I will have a transition over here and I will come to the middle. Okay, so let's say it's a negative, I will go back to positive. The next bit is actually 1, which means that I won't have any transition. So I will remain at this level and at the middle, I will go back to the negative. Again, it's a 0. So 0 indicate there will be a transition. So therefore, I will come up here. Okay, and then after that, going to the half bit, I will return back again. So again, the next bit is actually equals to 0, which means that I'm going to have a transition. Okay, so after that, I will return back here again. After that is message 1, which means that it will be the same, no transition. So therefore, I will have this waveform. And basically, you can see that I actually has indicate this no inversion or inversion means that whether there will be transition or not. So the next bit, if let's say it's 0, okay, I'm going to have a transition as you can see from here. If my next bit equals to 1, I won't have any transition as you can see from here. Next bit is equal to 0, and you can see that I will have some form of transition, etc. So basically with this, you can imagine that why it is better in terms of noise immunity as compared to Manchester. It's because I mainly look at whether there will be transition. I'm actually not looking at the level. I'm looking at whether they have some form of transition. If there is, okay, basically I will say that the next bit should be equals to 0. If there's no so-called transition, my next bit will be equals to 1. So this is actually for differential Manchester. Let me come to the last line coding, which is bipolar. Okay, so one of the example of bipolar will be this AMI, alternative mark inversion. Okay, so basically this is actually quite similar with pseudoternary. Okay, but I will explain later on. So for bipolar, they actually use three voltage level: plus volt, zero, and minus volt. So basically early on, okay, majority are using two level, but for this bipolar, they are actually using three level. Zero will be represented by zero voltage. One will be indicated by either plus V or minus V. So basically, this is for bipolar. Coming to the advantage of bipolar, okay, basically for this bipolar, you don't require any DC components. And if let's say if you have long strings of one, okay, basically you will be still so-called remain synchronized. Okay, so basically this is also the advantage of bipolar. Next will be on the error detection. Okay, you are going to have a violation of the alternating rules that indicate an error. Okay, so basically this I will touch on the later on video. Coming to the negative side, basically if let's say I'm going to have a long strings of zero, then I will still have a chance to have so-called loss in terms of time synchronization. But long string of one, I'm okay. But let's say long string of zero, I will still have this effect of losing in terms of the time synchronization. So they are actually used in the older T1, E1 carrier system with addition scrambling. Okay, I come into more detail on this bipolar. Okay, so for this bipolar, as I mentioned here, there are actually three voltage level: positive, negative, and zero. As you can see from here, positive, zero, and negative. So this is actually for the bipolar scheme. The voltage level for one data element is at zero, while the voltage level for the other element alter between positive and negative. Okay, so I come to this, okay, on this time diagram in order for you to understand better. The first example of bipolar will be alternative mark inversion. Okay, basically a neutral zero voltage represent binary zero, while for binary one, they are going to alter between positive and negative. Let's take a look on this diagram in order to understand better. For example, when the message is equal to zero, I'm going to indicate by zero. This is what we call the zero voltage here. And then let's say the next message is one, I'm going to so-called indicate by positive. Okay, as you can see from here, a positive level. And again, the message is equal to zero. I'm going to remain at 0 volt. And again, I'm going to remain at 0 volt for the next bit. But for the next bit, when it's message one, okay, instead earlier on is a positive. So now I need to switch to negative. So this is the meaning here, altering positive and negative voltage. So this is actually for AMI, alternative mark inversion. The next one that I'm going to explain will be pseudo-rarity. Basically, this is actually quite similar with AMI. In fact, they are actually opposite of AMI. So when the bit is actually equals to 1, they basically will be encoded as 0 voltage. When the bit is actually equals to 0, they will altering between positive and negative voltage, similar with AMI, but the reverse of AMI. Let's take a look on this diagram in order to understand better. Let's say the message is equal to 0. Okay, basically, let's say the first one, I'm going to indicate with positive. When the message is equal to 1, I'm going to have 0 voltage to indicate. So the next one will be so-called bit number 0. So I'm going to alter from high to low, from positive to negative. So basically, this is how I draw this waveform here. The next one will be bit 0. Again, I'm going to alter from low to high, as you can see from here. The next one is actually voltage 1. Okay, basically, I'm going to have so-called 0 voltage to represent bit number 1. And then next one will be 0, which means that I'm going to alter from high to low. So this is actually for this method, virtual polarity, which is actually opposite of AMI. The bipolar scheme is actually another alternative to non-return to 0. Okay, so this scheme actually has the same signal rate as compared to non-return to 0, but there is no DC component as one bit is represented by voltage 0 and another one actually alternate every time. What does I mean this? Okay, so basically if you still remember, okay, for those that have transition in the middle, they are going to have more bandwidth because they need to do this transition in the middle. So this is actually the disadvantage. But for this method, as you can see that they won't be having any transition in the middle of the bit. But how, in order to maintain the time synchronization, you can see that, for example, for this case here, they will actually alter, okay, when the message is equal to 0, which means that I won't have any issue. Let's say the message is a string of 0 because I'm going to alter over here, as you can see from here. Let's say the data bits is actually all 1, then I will have the same issue, okay, because they are going to remain at 0 voltage here. So this is actually for the bipolar. So over here, okay, I have described the line coding, okay, which include the unipolar, polar, and bipolar. Guys, before I continue, I'd like to urge you guys to help me by like this video. Guys, just give me a few seconds. Help me. Press the like button now. For those who are new to this channel, and if you want to encourage me, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Let's come to my last part of today's presentation. Okay, so I'm going to discuss the advantages and also the disadvantages of the different types of line coding. This page mainly will be for the unipolar line coding. Let's come to the advantage. Okay, so basically for unipolar, it got to be the simplest receiver circuit. This is because it is only on and off. Okay, so the receiver circuit for unipolar line coding is simple as it only needs to detect the presence or absence of a voltage. If you still remember, it simply works like an on-off switch. So basically, they need to detect whether it is on or whether it is off. So therefore, the receiver circuit will be the simplest one. Low DC component. The unipolar line coding scheme in fact has a low DC component which is desired for some communication system. Next will be low cost. Unipolar line coding schemes in fact use only a single voltage level, a positive voltage level. Another one will be 0. So therefore, it is easy to implement and require fewer components. This makes it a very cost-effective solution. Coming to the disadvantage of unipolar line coding, poor noise immunity. The unipolar line coding scheme has poor noise immunity, and basically they are actually very sensitive to error as it does not have a differential signal. Next, we are going to have a limited dynamic range because it's only so-called one level. The other level will be the ground. So therefore, the unipolar line coding scheme has a limited dynamic range as it use only positive voltage level. So this is actually for the unipolar. Next, let's come to the advantages and also the disadvantages of polar line coding. Let's focus on the advantages first. Okay, so for polar line coding, it in fact has higher noise immunity. Okay, so why? Because the polar line coding scheme in fact will be more noise immunity because it uses a differential signal. For example, differential Manchester. So therefore, it actually has a high resistance against the noise. Next will be the error resistant. Okay, so again will be the same reason. Okay, because the polar line coding, they are actually less so-called sensitive to error because it uses a differential signal. Let's come to the disadvantage. Okay, for polar line coding, it's going to have a complex receiver circuit. Why? Okay, instead of just 0 and positive, for polar line coding, we are going to have positive and negative. Hence, the receiver circuit for polar line coding, they are more complex as it need to detect the positive and also the negative voltage level. Limited data rate. Okay, so the polar line coding scheme in fact has a limited data rate as it requires a larger numbers of bits to represent the same information as the unipolar or bipolar line coding scheme. If you still remember, for polar, basically one bit is separate into two positions with a transition. The transition is mainly to synchronize the data, and because of this, we are going to have the twice the bandwidth, and therefore, again, because of this, we are going to have a limited data rate. Let's say we are going to send the same information, then this method, polar line coding, is going to have so-called limited data rate as it requires 2 times the data rate as compared to the rest of the line coding. Last but not least, bipolar line coding. Again, there will be advantages and also disadvantages. Let's come to the advantage first. Okay, so this will be able to support high data rate. Okay, the bipolar line coding scheme in fact has a high data rate as it uses positive and also the negative voltage level to represent the digital signal. The differential signal. The bipolar line coding scheme use a differential signal which improve noise immunity and also the error resistance. Coming to the disadvantage, again, okay, we are going to have a complex receiver circuit. Okay, so the receiver circuit for bipolar coding is complex. Okay, because okay, beside the positive and negative, it also need to detect the zero voltage level. Hence, it is more challenging to design the receiver circuit for bipolar line coding. Next, we are going to have a limited dynamic range. The bipolar line coding scheme, in fact, has a limited dynamic range as it uses both the positive and negative voltage level to represent the digital signal. With this, that's all I have for you guys for this Series A and Series B discussion on the different types of line coding. So on my last part, I simply explained the advantages and also the disadvantage of the different types of bipolar line coding. With this, that's all I have for you guys today. Thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.